what success looks like. I want to make sure everyone can see my screen.
We can see it.
All right. So for session 3, we're going to have 6 speakers, and they're each going to be speaking for just 5 minutes each. So this is our short burst with some just quick success stories from different people in our industry. So we have a few people from structural engineering consulting, and then a few people from the supplier side. We're going to start with Lindsey, who's a structural engineer, and then go to Max at AISC, Brandon at NRMCA, Michaela Harms with Sterling Solutions, representing the mass timber industry, Chris Magwood with RMI, and then ending with Sean from Arup. So we'll get started with Lindsey.
Thank you, Brenna. So today I'm going to be talking about communicating all of this with our client. And I saw some comments and questions on the last session about GWP and how do we look at that. And I would say I agree. Our firm has switched to a GWP way of looking at things. But a couple of years ago, we started tracking all of the embodied carbon on our projects and found this to be a very effective tool in communicating with our clients, kind of pushing in that direction when they can see the real numbers. So today, I'm going to talk about one project specifically and how we have tracked this through the projects. This I created in Excel, but we've been using Power BI as a way to show decision making in a project and how we can toggle through different mixed designs. So specifically looking at concrete in the project. Concrete was 45% of the embodied carbon for the building when we first looked at the building, even though it was a steel building, because of mat foundations and other things that came into play. So what I am showing here is the total carbon we had on the project. We started out with the baseline based on the CLF baseline, and that would be at 100% DD based on the volume of carbon that we had. Our standard my standard specs for GWP maxes immediately took us down by 30%. This was something that was easy to communicate to the client of putting that into the specs and the higher replacements that we wanted to target based on our region. So this is very regional specific, but in the Bay Area, we have access to a lot of great options. And so that right off the top took us down 30%. But we wanted to start shaving further. So that additional 6%, which is a relative change from DDs to CDs, was through a lot of collaboration. We, like I said, had a mat foundation. So we looked at removing the topping slabs. This was in a lower area, more back of house. So we had additional coordination with mechanical, architectural, and everything to get rid of a 5-inch slab on grade and use the mat slab as that finished floor. We additionally worked with a geotechnical engineer to allow for some increases in bearing pressures and things like that to thin up the slab on the upper floors. And so the change from that DD to CD, that 6%, is just in optimization of the structure and a pure removal of concrete, which is a great change. Again, no cost to the owner, just a couple extra phone calls here. The next change, which took it a further 8% down, was through meetings with our supplier. This is something that I require in all of my specs. It's just a 1-hour meeting to have a conversation to see what they have available, where I can give on maybe strength gain or other things at no cost to the owner to make an additional change. And through that, we took it down another 8%. One thing I didn't clarify, each of these bars is the structural material. So that lower bar is the mat foundation, just to see that change that you have there. And then the final change, that additional 3%, was the cost to the owner. And it might seem like 3% is only a 3% change, but that was a cost that we wanted to explore. And Brenna, if you can go to the next slide. So what we were talking about was a ton of the amount of savings. And so we found that for this mix, it was a $4 increase in the cost per cubic yard, which came out to $2,500. For reference, this was a $50 million project. So $2,500. I think the first comment I got was it's going to be an increase. And my question was, well, how much? $2,500 was somewhat of a drop in the bucket on a $50 million project. And it, in the end, and was covered by the owner's contingency, so they didn't actually pay out. But we, for the owner, extrapolated how many tons of CO2 they were saving, how that relates to gas, and things that they could understand. And it made a very easy, compelling conversation with the owner that they easily approved. I did see a comment, as I mentioned last session, on GWP. We did look at going even further on a percentage replacement. However, the GWP was actually higher, and so we did not make that change. So it's very important to look at the GWP on the mixes as well. So my takeaways is take the lead. You need to be in that room. You need to drive that decision and help bring everyone together. This was easy for me, I will say, on this project because everyone had a goal of getting to the lowest carbon we could. But certainly make sure you're in that room, reach out to the other disciplines you work with, and see how you can use metrics to show your owner the savings that they're going to have. So that is my takeaway.
Thank you, Lindsey. All right, we're going to move on to our next three presenters who are from the supplier side. So we'll start with Max from AISC.
Yes, thank you, Brenna. And hello, everybody. Good afternoon. Thank you to SEI for hosting this event. And we're going to talk about steel first to get us kicked off. There's so much to talk about with steel, but we just have 5 minutes per person. So I'm going to jump into what I want to make sure every structural engineer on this call knows about steel in these 5 minutes. So we talked a little bit before about resources, and when you try to think about the buckets or tools that structural engineers have to influence their projects, it falls into a design bucket, it falls into a specification bucket. And naturally, you talk about specification guidance and design guidance. And before jumping into my specific recommendations, I would be remiss without having another plug for the SE 2050 resources on their website, as you can see here under the drop-down menu. And the other reason I want to endorse these is because in addition to the advice you will get from people like myself and other people in material industries, is that the specification and design guidance here on the SE 2050 website was developed in conjunction with and collaboration with and vetted by all the structural engineers on those resources, on that resources group. So you have another added layer of value in those. Next slide. And I'm going to talk specifically about specification guidance because for steel, I find that that's the one that it has the larger amount of value or possibility for embodied carbon reductions. All right, this is a sneak peek of a document that, hold on one second, a sneak peek of a document that's going to be published by AISC in the next couple of months. As you can see, it is specification strategies for structural steel embodied carbon reduction. And we're going to have 6 different specification strategies that folks can evaluate on their own for reducing embodied carbon in their structural steel packages. I'm really excited about this document, and I'm very eager for it to be published because in addition to providing sample spec language and building on the work of the SE 2050 group, it's also going to come along with a whole lot of commentary and context and recommendations from AISC directly. And for each one of these strategies, you'll be able to look at them in particular and try to figure out what makes sense for you and your projects. I'll quickly just highlight the 6 strategies as we kind of go along here. The first one, as you can see, is environmental product declaration disclosure. This is what everybody should be doing. Whether you're a part of SE 2050, if you have any sustainability inklings at all, this should be happening for all of your materials on all of your projects. For steel, you can get a really great summary of all of the available domestic facility-specific EPDs in the whole country at aisc.org/EPD. If you are a structural engineer on this call and you care at all about sustainability, please bookmark that website, as it'll be extremely helpful for you to see them all in one place, correctly interpreted and summarized. Next. Number 2, sustainable fabrication. So AISC launched a partner program for our member steel fabricators in the past year or two, and we are listing all of those fabricators on our website dynamically who are in the program. So you can see which fabricators in your region are a part of the program and have made the commitment to sustainability, both for their own operations and their own footprint, but also they've taken the steps in order to get educated on sustainability, to be a sustainable partner on your jobs, because of course the fabricator is the one who's buying the steel on your jobs. They're the only one doing that. So they need to know what you're talking about when you have sustainability goals. Next. Number 3, domestic sourcing. That's obvious because on average, just for about every steel product out there, the US average footprint is much lower than the global footprint. Next. EAF sourcing, I believe most people understand there's 2 different types of steelmaking, and EAF sourcing generally has a lower carbon footprint than integrated steelmaking. So this has, still on number 4 there, this has varying degrees of value. You know, some products are 100% EAF already in the States, but other products you'll still see a mix of BOF and EAF products out there. So making a simple differentiation makes a lot of sense for certain products. Number 5 right there, global warming potential limits. So that's certainly a very popular approach. We have guidance in there for what we would recommend the particular thresholds to be relative to common baselines and relative to project and cost implications. And lastly, recycled content minimums. This is actually an approach that we don't recommend, but we are including it in the specification strategies document because it is such a prevalent approach that I see in people's specifications all the time. There's reasons for that, why I think it's a bit of a lingering idea in people's minds. So for people that still want to have it in there, we have it, but we're also providing some commentary and context on that approach. And then one more click. And what's the point? Always important to ask. Oh no, go back one, please. And what's the point? So when we talk about embodied carbon reduction strategies, and this is addressed in detail in the document, it's really important to understand, you know, are we doing something on paper to make yourself feel good, or are we having a real world effect on embodied carbon reductions? And we provide commentary about each one of these approaches about how well they're actually sending a strong market signal to industry about the importance of decarbonization. Because unlike concrete, for example, where the engineer has a lot of control over the mix, right? You actually don't get to decide what the metallurgical makeup is of the steel you buy. So instead, the approach here is that how well are you providing that strong market signal to industry and to drive and invest in decarbonization industry-wide. Okay, next. And then lastly, I'm really proud to say that, you know, on the steel front, steel is the material where the data is available to you. This is an analysis by the EPA in preparation for their some of their Seymour programs, which is another topic. But they concluded that you can see on the second one from the right there on steel, that includes rebar as well. The coverage of facility-specific EPDs for steel products is extremely good, both for facility specific and for industry wide. Every single steel product available to you has an industry wide EPD available so that you can do both your pre-design and your specific design measuring your baselines. So when you think steel, think availability of environmental data that's there for you. And then you can click through the next few. Make sure you bookmark, back one. Make sure you bookmarked all of those pages too, because that's exactly where you're going to find all of that data all in one good place. Thanks.
All right, thank you, Max. All right, next is Brandon with NRMCA.
Greetings, everyone. Happy to be here. Obviously, only got 5 minutes, so get your snipping tools ready. I'll do my best to fly through this. A lot of content, and as you can probably imagine, looking at the previous presentations, a lot of opportunity with concrete. A lot of opportunity for things to go good, as well as things to just be stagnant and not go the way you want because little simple steps were not implemented. So my big thing that I want to touch on today is kind of 2 critical things that you can really focus on, or I think sequential things you can do. First is kind of that incorporation of a performance-based specification, which is kind of a ambiguous term to some groups, but I'll highlight some examples there. Second is really triggering the use of low carbon concrete, versions of low carbon concrete via setting a carbon budget for the project or just setting carbon goals, that type of thing. So what is performance-based specifications? It really is just as simple as a transition from historical prescriptive approaches and your specifications or your structural notes where you're listing your mix tables and you have certain criteria in there that are basically dictating how the mix design should be made, what materials should be used, proportionings, all those types of things. A lot of it kind of stems from the good intent of wanting to have some positive benefit on the concrete mix. But as we transition into an age of one, stronger communication between the producer and the engineer and the contractor, as well as better codes, building codes, those types of things. There's a lot of unnecessary things I see in specifications. So transitioning from a prescriptive version, which is that ideology of describing or telling the producer how to make the mix, into a stage of just dictating what you need performance-wise. So the crux of this is really just emphasizing ACI 318 exposure classes. Those are the only real instances, I think, where you should say, and it's a good thing to say, hey, we have a durability concern, and so we're going to put in a specific water to cement ratio, whatever it happens to be. Those is just where you should always default to when you're actually setting up your specifications and your general notes. There are other things that are out there, such as alternative testing for durability. People don't really realize this. When you have, say, chlorides in your soil, you think you need a water to cement ratio requirement. That is true, but there are alternate tests that you can incorporate that can circumvent that water to cement ratio and get a more efficient mix with maybe a higher water to cement ratio, but the same performance. Things along those lines: shrinkage, modulus of elasticity, rapid chloride permeability, and alkali silica reaction. A lot of things there. On the right of the screen, you'll see our guide to improving specifications, as well as this engineering sheet and our top 10 ways to reduce concrete's carbon footprint. Give those a look. The specification document is definitely a 3300 guide that you can use and even put in the entire thing into your project if you'd like. But the emphasis there is, one, on incorporating these types of things, but also two, expanding the list of acceptable materials. If you're listing just ASTM C150 cement, you're technically really precluding the use of, say, a blended cement that is lower carbon, those types of things. And another thing that I find, the main thing, if you were to take away from this whole conversation here with me today, is the simplest thing you can do is extending strength development. We're fixated on this 28-day figure. Let's transition into, say, a 56-day or 90-day, wherever applicable, where you can apply that. Next slide. Prescriptive specifications, like I said, this is kind of an example of what I'm talking about. There's the good and the bad, the good being durability and code-based. You get that mix table. I didn't share it here on the screen, but I think most of us are generally familiar with that. Use that as your guide. Apply the exposure criteria and their classifications as you see fit, but not unnecessarily is kind of the main takeaway there. On the right there, you do see a survey that we did with ACI on specifications, and you can see the frequency of these unnecessary prescriptive requirements and projects. I review specs every day, all the time, and I don't think I've ever really had a spec show up on my desk that didn't have something unnecessarily in it that was inhibiting the efficiency of the concrete mixes. So you can see across the board, they all generally reduce sustainability, generally increase cost, and their benefits on performance can be kind of a wash, right? So avoid those when necessary. When you have such things as like special properties that you desire, crack control, finish quality, other mechanical properties, there are other things you can incorporate. Shrinkage, and don't put in a water to cement ratio, but instead put in shrinkage percent or strain, whatever it happens to be, things along that nature. And the reason that this is so important is that people think when you specify on that little bell curve you see on the bottom there, when you specify 4,000 PSI, you think, oh, I'm going to get 4,000 PSI. The reality is we have to account for environmental conditions, delivery conditions, all these other variables. So the reality is you do get a mix that is above that, so that we minimize the situation of in situ strength that is below the specified design strength. But when you add all these additional criterias unnecessarily, it only pushes that bell curve in the wrong direction. Next slide. So really the crux here is don't limit ingredients, pull out unnecessary water cement ratio limits, cement content requirements, cementitious types, SCM contents, all those types of things. Instead, default to exposure class, broaden the list of acceptable raw materials, alternative testing, and later age strengths. I do have a document I can share with the group as they see fit that kind of shows an example mix table where it emphasizes, you can see there on the right, 56 days, 28 days, kind of bobbing and weaving as you see fit. exposure classes, only putting water cement ratio when it is dictated by the exposure class, as well as notations for shrinkage and other things like of that nature. So keep that in mind. Next slide. And last here is just the one thing about performance-based specs is they don't require, SCMs or other types of low carbon mix by mix strategies. They allow for it, but they don't require it. It's kind of the notion that we're trying to go for. We don't want to be overly prescriptive with our sustainability as well, because different producers have different materials, different strategies, different regions, different climates, different times of year. There's a million different variables that you can't really control. So really set what we call a carbon budget for the project. And all that is just one, collecting EPDs, and two, taking a look at your structural takeoff, establishing a benchmark project. If you're familiar with NRMCA, we do have the benchmark for the industry. Use our document for that. And then compare it to a proposed projects. And we have a lot of resources on our website that you can take a look at that walk through what a carbon budget looks like, and we do separate presentations on that. But the results is really just the procurement of low carbon concrete, but more specifically, flexibility for the contractor and producer to execute as they see fit, put low carbon as best they can into the foundations, and maybe not so much in the post-tension decks and the slabs, that type of thing, right? Giving them that flexibility to account for as-built conditions and other environmental things that they can't control. And that's it for today. Thank you.
Thank you, Brandon. All right, next we're going to switch to Michaela, timber industry.
Wonderful. Thank you. Well, I'm definitely going to repeat some of the same things of what the mass timber industry is looking for, similar to concrete and steel, and how we can work best with you. But a lot of our initial sustainability things come down to fiber sourcing. So your specification details really matter there. We as an industry would love to move also more towards a performance-based specification because of what's really available on the market. And so the typical thing that we talk about are our certifications in general. So Sustainable Forestry Initiative, Forest Stewardship Council, there's many that are out there. But the first and foremost thing is keep it continental. US and Canadian forestry is extremely sustainable forestry. Our forests are growing. 80 to 85% of our lands that can be forested are forested and continue to be forested. So that's what we know on the continent and what we want to continue to support. So that's a great thing to put into your specifications. When it comes down to the specific species, it's important to be a little bit careful and maybe move more to that performance base. So if you can have just the bare minimum here, and then of course we'll talk about it with the architectural teams as far as the look, but it opens up the supply chain a little bit more because sometimes when you get into these very specific things like FSC, SFI, only, or spruce pine fir or southern pine only, you're going to have some limitations in the supply chain. Next slide, please. And just like our friends in concrete and steel, we're working really hard to make more data available. So definitely ask for data. If you're doing your whole building LCA, almost all of the mass timber manufacturers have manufacturer-specific environmental product declarations now. There are industry-wide ones available as well if you're working with a smaller manufacturer or something like that, available from the American Wood Council. And then just recently, the American Wood Council has released life cycle assessments of our forests per kind of per region. So at this time, the manufacturers are updating all of our EPDs to that more regional forestry model. So we're only getting more granular with our data, which is where we want to move. And then, of course, all of us have declare label if you're going more towards the living building challenge and transparency section. So put those things into your specs, ask it out of us. The more you push those in the specs, the more the manufacturers will continue to provide these things. Next slide, please. And then it's really important to say that, the wood products industry is inherently a very low waste industry. If you come into any of our plants, and we always invite people for plant tours because seeing is believing, there's almost no waste. And any waste has a secondary market and tertiary market, whether that's combined heat and power, or maybe it's, animal bedding as it goes all the way down to sawdust and flakes. So there's a lot of really great opportunities there where we're always kind of regenerating that supply chain or putting maybe even into a compostable situation. But it's really important to think from a design for manufacturing perspective. So yes, you can make all these great shapes and things with wood because of our CNC capabilities, but it's best to stick to the rectangle as much as possible. So offering more repeatable, standardized grids is going to give you not only the most cost-effective system, but the most waste-limiting system, which is great from the sustainability perspective. And then understanding the efficiencies of your manufacturer specifically. So every manufacturer runs on a different billet size. And so, you know, as you get into these projects, make sure to speak with your manufacturer and ask them those types of questions to know where to start. Next slide, please. And that modular thinking not only helps from the design perspective, but also from every way that we deliver. And when we talk about the fabrication piece, you know, a lot of times we talk about prefabrication in mass timber. Understand where it's necessary and where you're able to get those things from your MEP engineers in time versus when it might delay the project or might be better done on site. So that's a nice flexibility tool that we have in our industry. And then understanding what layups are available is really important. The PRG 320 performance standard for cross-laminated timber and A190.1 for glulam do specify specific layups. And there's kind of a massive abundance, and you can do lots of different custom ones. So if you're designing to one very specific thing because you're trying to make that plate as thin as possible, just understand that that might really extend your timeline and maybe not get you the sustainability benefits that you're looking for. So looking more from that performance-based specification and also working with your manufacturer to see what's the most common layups they make so that they're really available. And then thinking very modularly is going to keep that waste down in the industry. Next slide. And then rounding that out, as everybody has said, specifications are your friend. So just really understand what the impact is of those specifications. So it's really important to balance the priorities of sustainability, speed, aesthetics, and cost, because ultimately you got to understand the end goal. We are working as an industry across the construction materials to continue to provide more environmental product declarations and more life cycle assessment data for you all. Forest certification is great if you can get it. Again, start with that continental mindset. It's like buying the vegetable in the first place. And if you can get the organic vegetable, great, but don't go over and buy hot dogs just because you can't get the organic vegetable. So it's important to just think about it that way. And then from the location perspective, you might see a really great EPD out of something in Europe, or they have the FSC certification, which the FSC certifications are different by country. Just understand that now you have this extra transportation cost included into that in your environmental calculations. And then what we always say is make sure you're asking questions of all materials. How are all of your materials sourced? Because I think sometimes we go into the Lorax syndrome and we really get kind of emotionally connected to trees. And we want you to be connected to it. We want to talk to foresters, but we want to be asking that sourcing question of every material. And because about 75%, Chris is going to start talking about carbon storage, about 75% of that stored or sequestered carbon in a whole mass timber building is in your decks and your floors and roofs. We tell you to consider hybrid. Consider using steel for your spanning members and consider using concrete. Use all of these materials together for the best solution that you can come with. And we always like to say, some wood is better than no wood. So we see that a lot where somebody says, I want all mass timber, and it doesn't quite cost out. And so we would really love to get everybody more to the hybrid and thinking about all these materials working together to get the right materials in the right spaces. And then an excellent opportunity is Woodworks. They provide life cycle assessment support for your teams.
All right, thank you, Michaela. We're gonna move on to Chris, talking about carbon storage. Thank you.
Great, thanks. Thanks, everybody. I'm not sure I'm here to talk to you about a simple win, but more, hopefully you leave with a simpler understanding of the notion of carbon storage. So if you can go to the first slide, please, Brenna. So I'm going to be specifically talking about biogenic carbon. This is plant-based carbon. And we're really talking about the carbon cycle that happens naturally on the plant, where plants draw CO2 out of the atmosphere via photosynthesis. And then in some short-ish amount of time, that plant matter decays, is eaten, it burns in some way, it goes back to the atmosphere as CO2, and that's the cycle that's been going on for eons here on the planet. If we go to the next slide, what we're really talking about with carbon storage is trying to put a gap in between when the carbon comes out of the atmosphere and when it goes back. And in particular, we're talking about creating that gap by putting that biogenic material into a building product and then into a building so that it is out of that carbon cycle, it's out of the atmosphere for more than the short number of years or decades that it would naturally do, but more into extended decades or even centuries by putting it into buildings. And the longer that gap is, the more impactful the carbon storage will be. But also, as you're thinking about carbon storage, whatever that gap is, if you're looking at a biogenic product that you think is going to be in the building for 40 years, if the product itself took 40 years to grow, the length of growing time really matters, as well as the amount of time that it's in the building. So we'll go to the next slide. I think there's a lot of confusion in the when people start thinking about carbon storage. There seems to always be this a sort of disagreement between the way life cycle assessment thinks about it and the way sort of dynamic life cycle assessment or sort of carbon valuing is. And they're actually two distinct things, and they're not in competition with each other. So there's counting carbon and there's valuing that carbon storage. So if we go to the next slide, I think the best analogy I've sort of come up with for these two different notions is counting carbon storage is just like simple accounting. It's like, I put $1 in my bank today, I take 50 cents out tomorrow, that leaves me 50 cents. It's, it's this very straightforward kind of accounting where you're saying, a certain amount of carbon comes into the product cycle, a certain amount of carbon leaves the product cycle. Therefore, it's that very simple kind of accounting. Whereas valuing carbon storage is more giving value to the time that carbon is stored, in the same way that we give credit to money for time. So if you go to the next slide, the counting of carbon storage is what life cycle assessment does really well. There's sort of no issues with how that's done. At each of the stages in a product or a building's life cycle, you're simply tracking, this much carbon came out of the atmosphere into this product, it stayed here, or a small amount left when a change was made, et cetera, all the way through the end, where at the end of the life cycle, some or all of that carbon goes back to the atmosphere. So that's the counting of it. The valuing of it says, okay, if that carbon came out of the atmosphere at this time and it returns at this time, what impact did that have on the climate? And that's where you get more into varying ways of looking at dynamic life cycle assessment. And if you go to the next slide, yeah, we're really talking, the difference between how much carbon moves around and how much value that carbon has. Now, just like with any sort of financial analysis, there are a lot of it depends that go with the time value analysis. And if you hear sort of competing notions about, the value of carbon storage, it's typically not that it isn't valuable to store carbon over time, it's how valuable is it? And I'll sort of, I may not touch too much on that. That's more than a 5-minute discussion, but I really want to sort of emphasize this notion that the numbers you see in a life cycle assessment or on an EPD are the simple accounting. That's the core information that you need. But if you want to apply a value to that carbon storage, you have to understand, what impact it's having on the climate. So if we go to the next slide, this is something generated out of a dynamic life cycle assessment tool. The graph you're looking at is the actual temperature change. So the numbers get very small of 1 ton of emissions when any product happens to be made. And you'll see another blip in that diagram where 100 kilograms comes out at the end of that product's life cycle. The whole area in pink is the climate impact, not just the line and the number at the end of the line, but the area under the line. On the right-hand side, you'll see if you take a ton of CO2 out of the atmosphere, the green section of that graph is cooling. It's out of the atmosphere for 60 years. If it's fully released at the end of the 60 years, you'll see that it does go back into the atmosphere, but its actual warming, the pink part, where it pops up above the line, is quite a bit smaller than the 1 ton of emission. So over that period of time, that storage of carbon had a positive effect, a cooling effect on the climate, where the graph is green, and a small warming piece where it's pink. Now, you could extend the timeline that the carbon is in the building to change that. You can change how much carbon goes back to the atmosphere, all kinds of things. But this is sort of the one look at how you can value that carbon storage versus just looking at the LCA numbers that go in or out. So if we go to the last slide, there's lots of factors to think about. There's the amount of carbon stored. There's the counterfactuals. What would have happened to that carbon-based material if it didn't end up in a building? Like I said before, how long it's stored in the building. All dynamic life cycle assessments are done based on a global emissions trajectory. It matters whether global emissions continue to rise, whether they drop, whether they plateau, and the speed they do that will change a dynamic life cycle assessment. And also the end of life assumptions for that carbon-based material. Currently we tend to think that it all pops out back into the atmosphere the day that the product is taken out of the building. But in fact, there are all kinds of different end of life scenarios that will also change the length of time and the value of that carbon storage. That's about as much as I can pack into 5 minutes. I'm glad if people want to sort of follow up and explore this notion more, and looking forward to the rest of this presentation.
Great, thank you, Chris. We're going to wrap up really quickly with Sean's presentation before getting to our closing remarks.
I'm going to talk now a little bit about some case studies of projects and how you can get some simple wins, even if your project may not have some stated lofty sustainability goals. So first one I want to jump in on is one that's local here to us in DC. And this is one where there was actually a lot of plaza work happening, and there was a huge area of elevated slab on foam that in some cases was 5 foot above the existing structure. And what we were able to do was look into some structural knee walls and some CMU block walls in the direction parallel to the deck, and use spanning deck rather than slab on foam. And as you can see here, that in itself got us an embodied carbon savings of about 150 tons of CO2 equivalent on this project alone. On that same project, we actually did a study on the use of normal weight versus lightweight concrete for slab on metal deck. Often lightweight is specified by architects to achieve desired fire rating. And so what we looked into was using the normal weight instead of the lightweight with a spray applied fireproofing underneath to get that same fire behavior. And we looked at various thicknesses of the normal weight concrete compared to the lightweight. And what we found was that we were able to use a 3.5 normal weight on 3-inch deck as opposed to a 3 1/4 lightweight, which we'd used before. So there is a slight difference in structural depth there, but very minimal. And even with the spray applied fireproofing included, we found that we could get about a 10% reduction in embodied carbon on this project alone, which was about 47 tons of CO2 equivalent. So as you can see, not quite as big as the elevated deck change, but still, pretty significant. And we've done some studies as well that, this in an all steel building, you could be saving up to 20% of the embodied carbon in the overall structure. So really something that we want to look into. And then finally, a project in DC where we specified a GWP budget for our for the overall concrete mixes on the project, and we mandated a 20% reduction across the board. And we found that we were able to meet that and I'm showing this pie chart here, which shows the structure as a percentage of the total embodied carbon on the project. And what you can see is that, it is the vast majority, at least of structure and enclosure, which is what's captured here. And the vast majority on this particular building is concrete. So achieving that 20% reduction in just the concrete mixes alone made a huge difference. And you can see here, 1.4 million kilograms of CO2 equivalent, so about 1,400 tons. Huge difference just by that one requirement. And we were able to do this without a significant increase in cost. And then one additional here, this is a large wastewater treatment facility that we were working on in Idaho. All steel structure, huge footprint, as you can see. And we were looking into the foundation systems and tuning the concrete strength to what was needed and try to achieve some cement reductions that way. And what we found was that having the footings go down in strength while having the pedestals go up, because there was a lot of bearing under the base plates, did actually achieve some optimization there. And we were able to take about 12% out of the embodied carbon in these foundation systems, which for a foundation of this coverage was pretty significant. So with that, I will turn it back over and just say thank you to all our presenters.